Recursion is an important concept in computer science, yet it is often challenging for beginners to wrap their minds around. Don't worry, it makes a lot of sense once you get it. Follow along with this tutorial and I will help you master recursion. In a nutshell, recursion is a divide and conquer method for solving certain kinds of problems. In this tutorial, we will use recursion to perform simple calculations, such as computing n factorial. We will also use recursion to compute the nth term of the Fibonacci sequence. In real-world applications, recursion is used for tasks like traversing through file directories. In order to benefit from this tutorial, you need a basic understanding of functions in C++ or some other semantically similar language, such as Java or JavaScript. In the video description, you can find a transcript and source code for this tutorial. In English, the word recur means to happen again. In computer science, recursion is a technique used to solve a problem in which a function calls itself. It might sound strange, perhaps like a snake eating its own tail, but it actually works. By calling itself, a recursive function can solve a problem with minimal code. With each self-referential call, the problem is solved in parts. Eventually, the function will stop calling itself. When the function reaches its base case, it will return a value for every function call. The return values of those function calls will be rolled into one large return value. In order for a function to be recursive, it needs a special conditional statement called the recursive case. When executed, the recursive case will have the function call itself. The functions below perform the same task, which is computing n factorial. Function A uses iteration or looping, while function B uses recursion. Every recursive function requires an exit condition, otherwise the function would run forever. We call the exit condition the base case. When the base case evaluates to true, the function will return an actual value instead of calling itself. In order to keep track of all these function calls, the program uses a structure known as a memory stack. Function calls are passed on to the stack and then popped off in the opposite order. Although recursion generally uses less code than iteration, recursion tends to use a lot more memory than iteration does. This is true for imperative languages such as C, C++, Java, and Python. If the recursive chain is too long, the stack will run out of room to store programmatic instructions. When that happens, we get a stack overflow. This would probably crash your computer. If you would like to crash your computer, try entering a large term in the following Fibonacci sequence function, and try running it on your computer. Unlike the factorial function in the previous example, the Fibonacci sequence function will take up exponentially more memory as the input value increases by just 1. Instead of forming a linear stack in memory, the Fibonacci function will form a binary tree. That is because each recursive case in the Fibonacci function makes 2 calls. If you want to compute the 0th term of the Fibonacci sequence, only one function call will be made since you are immediately exiting the function through the base case. If you want to compute the first term of the Fibonacci sequence, you will make a total of 3 calls to the function since you would enter the recursive case, which calls the function twice. If you want to compute the second term in the Fibonacci sequence, you would call the function 5 times. In general, the number of function calls pushed to the stack in the recursive Fibonacci function is 2 to the n plus 1, where n represents the count of the Fibonacci term. To save time in memory space, you can create an array that saves the terms of the Fibonacci sequence in order up to some maximum number of terms. You can run a modified version of the Fibonacci function just once and store all of the terms of the sequence up to n. Then, whenever you need some term in the Fibonacci sequence, you just retrieve it from the array instead of computing the result. Technically, the time it would take to retrieve an element from the array would be time O of 1. In another computer science tutorial, I will go over algorithm efficiency and big O notation. Thanks for watching this video. To see the transcript and source